laws. Okay, so let's start. Welcome everybody to the webinar of today. The speaker of today is Martin Oberlack, and the topic of his talk is turbulent scaling laws of high moments in wall-bounded shear flows. As usual, I introduce the speaker very briefly and then I leave him the stage. So Martin Oberlack is professor of mechanical engineering at Darmstadt University and holder of the chair of fluid dynamics. He received his bachelor degree in mechanical engineering from the University of Essen in 1985. His diploma degree he obtained in 1988, his PhD degrees in 1994, and his habilitation in 2000, all from RWTH Aachen. He joined the TU Darmstadt Faculty of Civil Engineering in September 2000. He changed to the Department of Theoretical and Applied Mechanics in 2005, and 1 year later he switched to the Department of Mechanical Engineering. He co-founded the Center of Smart Interfaces at the Graduate School of Excellence Computational Engineering at Darmstadt University. He has been actively involved in the editorial boards of theoretical and computational fluid dynamics and continuum mechanics, thermodynamics, and fluid dynamics research, for which he is an editor, and he recently joined the editorial board of Communication Physics Nature. He's presently co-editor of 2 books series, Mathematical Physics Theory and Applications, and Progress in Turbulence, Fundamentals and Applications, Spring as publisher. His refereeing activities include almost 50 international journals and nearly 30 national and international funding organizations. Professor Oberlack is a member of the American Physical Society, of which he is also an elected fellow for his pioneering use of symmetry methods for the study of turbulence and related fields and the derivation of new conservation laws in fluid dynamics. He is also a member of the German Committee of Mechanics, the International Association of Applied Mathematics and Mechanics, the European Mechanics Society, the European Research Community of Flow, Turbulence and Combustion, and the Society for Industrial and Applied Mathematics. So it's with great pleasure that I introduce Martin Oberlack for his talk. So Martin, I stop sharing my screen and you can start sharing yours.
Right. Yeah. Many thanks, Francesco, for your very kind introduction. Now, let me just try to share the screen here. That I guess seems to work.
There we go. We see your screen in full mode.
I see. Give me 1 second here. I have to deal with the second screen. Okay, that's fine. Okay, so welcome everybody. I feel very much honored here to be here on this distinguished seminar. And I will be talking about turbulent scaling laws of high moment of wall-bounded shear flows. In fact, at the very end, I will also talk a little bit about PDF, but this is very briefly. I would like to mention my co-authors, which is Professor Sergio Hoyes. He is from Polytechnic de Valencia. Stephanie Pragerberger, she is a PhD of mine. Francesco is also a postdoc of Sergio, and Jonathan Laukes is a master student of mine. Okay, so let me just first give an introduction here. And when we think of wall-bounded shear flow, very often, of course, we have some classical scaling laws in mind. I mean, for example, here, that is a boundary layer flow. And if we consider the near wall region of this flow here, of course, there is the very well-known law of the wall. And that was derived in kind of combination of von Karman and Pruntel. And they came up with this an equation here. And then, of course, if you non-dimensionalize, you get this equation here. And apparently, when we compare that to data, that seems to work pretty well here over, well, depending on the Reynolds number, over several decades, actually. The key question is, or the key point is, when you look at the derivation in various books, there's absolutely no connection to Navier-Stokes whatsoever. So the question is, do we have a first principle machinery that allows us to derive such a scaling law or to derive scaling laws in general? So the motivation here is derive high order moments, not only the first moment, that is the mean velocity, and also PDF scaling laws from Navier-Stokes. And we would like to look at certain regions. That is, one of them is the log region and the near wall, and the other one is the core region or deficit region in the center of the channel. And for that, we actually conducted a very large DNS at the order of RE tau of 10 to the 4, that in order to very clearly see the different scaling laws. That was, so to say, the motivation of the work. However, in order to understand at least a part of it, hopefully most of it, we need to introduce some concept here, and that is the concept of symmetries. So when we think of symmetry or a symmetric object, I mean, we think of really something that we use every day. And for example, we look at the cylinder here, and we would probably call this a symmetric object. And the reason is because if you would rotate this object here, the cylinder, it looks the same. So there is a certain action that we impose on an object, and the object is the same. Mathematicians have used exactly this concept and applied that to equation. In particular, they applied that in physics to differential equations of physics. So suppose you have a differential equation here, x is the independent, u1, and so is dependent variables and derivatives. And that could, for example, be Navier-Stokes, but anything that you like. Now, if you are in the position to find a transformation to a new set of variables, we call it x star and we call it u star. Now, if you take this transformation here, x star depends on the old x and u star may also depend on the old x and u. Now, if you take that, plug that into this equation here, and if as such that you find a transformation that the equation looks the same, then you have found a symmetry transformation. To make that a little bit more clear, let's look at a simple example, and I usually like to use the heat equation. This is the one, the heat equation, time-dependent part here on the right, and the heat conduction part on the right-hand side. The heat equation, in fact, has 6 known symmetries, or there has only 6 symmetries. However, we just want to look at 2 of them. The first one is scaling of space. So we have a factor e to the a1 here, and the scaling of the same factor but squared, a to the 2a1. And independent of that, we scale the temperature, that is e to the a2. Now, we call this a symmetry transformation. In this case, it's a 2-parameter scaling group. Now, if we take this transformation, put it in the equation, and then what we observe, of course, is that the scaling factor drops out on both sides, and exactly we achieve what I was just said earlier, that this equation is form invariant under this transformation. It essentially looks the same as the original equation now written in the star variables. That is the most important concept, the invariance of equations. The second concept here is what we call an invariant. Now, once we have such a symmetry, or a 2-parameter symmetry, we can construct quantities that also are invariant under this transformation. So for example, this x tilde here, which is just x over square root of t. Now take the transformation and you can easily see that the scaling factor drops out. That means you are left with the star quantities, and that is x tilde star. So this apparently is an invariant under this transformation. In the second step, we might derive a second invariant, and that is the one that also contains the temperature. So take that quantity here, do the same thing, introduce the variables and transform to the star variables. Again, what we observe is that these factor cancels out, and we find this is what we call an invariant. That is a second important quantity and concept that is needed then to construct solution. And that is what we call invariant solutions. That is a classical idea. In fluid mechanics, we have an enormous amount of different solutions. Probably the most well-known one is the Blasius solution. So essentially what you take these invariants here, put them in the original equation. So x star, then x tilde is here the new independent variables, and t tilde is the new dependent variables. And if you do so, of course, you get what we call the reduced equation. In this case, we do have an ODE, which can solve in terms of the error functions. A final concept that we need later is what we call symmetry breaking. So far, we have only spoken about differential equation and not about boundary conditions. Now, let's assume that we have a boundary condition. So at x equals 0, we assume that there is a fixed temperature. We call it T0. Now, if we take these scaling symmetries and introduce them here, well, we do see that the scaling of the space variable now in the x star quantity is 0. It doesn't change it. However, here we do see that having the boundary conditions form invariant, it does not work for an arbitrary A2. That means A2 has to be set to 0 in order to also have the boundary condition form invariant. And also, but the A1 remains undetermined. That is, so to say, a scaling that could be used. So what we call here, or what we say is T0, so an external quantity, the boundary condition, or whatever you like, is symmetry breaking. What do we know in terms of symmetries of Navier-Stokes equation? Well, I will not discuss all of them. What we really know and what we need later is essentially the scaling of space. So please keep in mind we have this A as x, the scaling of space. That means also scaling of the velocity and of course the pressure, or this is pressure over density. It's also a factor of 2 here. And we have a scaling of time, that is this AST here. That means we have to inversely scale velocity and also the pressure. However, be careful. This is in principle only true if Reynolds number goes infinite. Of course, there's many other groups, Galilean group, rotation groups, some special groups for 2D flows. What we know, all these symmetries transfer to statistical equations, no matter what that is. Maybe the Reynolds stress transfer equation, maybe that any multi-point equation, if the Hopf functional equation is invariant under these symmetries. Of course, if that would not be the case, of course, we would be out of classical mechanics and we would not be dealing with Navier-Stokes in a sense. Now, let me go now to the next point, that is the statistical description of turbulence. What I will do in most of the rest of the talk, I will talk about moments. So let's first define initial instantaneous values, that is the capital U and capital P. Then we have the classical mean values, that is the U bar and the P bar. And of course, the sum with the fluctuating quantities U bar plus the fluctuation of P bar, of course, gives the instantaneous values. That, of course, then can be used also in the 2-point sense. That means we can derive or we can define a 2-point tensor classically. So we have the velocity fluctuation Ui at this point here and maybe Uj. At this point, there is a difference between the 2 points, that is R, and then we can define what we call as the Rij. That is the classical 2-point tensor based on the fluctuations. However, we will later see this equation here for the 2-point tensor based on the fluctuations is a very ugly equation. It's much easier if we do the following. Let's assume that we derive the correlation, the 2-point correlation tensor based on the instantaneous values. That is Ui, capital Ui and Uj, and this is what we call the H approach. That is essentially based on the instantaneous quantities. Why is that important? And why is that helpful? Well, what we can do is we can generalize that. So you can write down a tensor, say, of arbitrary order n+1, I call it here. That is, so to say, the tensor order. So you have all these indices here. And you can write down an equation for that. And classically, in most of the classes, what we do, we just take Navier-Stokes equation, then we multiply by the respective velocities at the different points. So we multiply that in and do the average, and then we get this kind of an equation. This equation is very special and very different from the R approach, as you will see in a minute, because it's an infinite equation, of course. So any tensor order n+1 contains terms of the tensor order n+2. Of course, that comes from the convective term. So it's infinite sequence of terms. This comes from the pressure, and that, of course, comes from the viscosity. So it's an infinite set of linear PDEs. And the coupling between these is only to the next order. Later, we will just look at this quantity. So this is just a 1-point moment. But for now, we just concentrate on 2-point. Now, what we had before is this quantity here, that classical one. You find that in any textbook. And now, if you write down an equation, even for the multipoint, it becomes very ugly. I mean, you do have, of course, the convective term, which is nonlinear. We got additional terms here, which is a kind of a production term. It's nonlinear. We get pressure term, but viscous term. But we also get a coupling. All terms, all equations are coupled to the Reynolds stress tensor, also nonlinear term. So this is an infinite set of nonlinear PDEs, and the coupling is among all orders. So this is a very ugly equation. The good news is they're fully equivalent. So whether you take the H approach or you take the approach based on the mean and the R, so for example, here the H, that is the second order tensor, it's simply in the classical notation, the product of the mean velocities plus, of course, the second order tensor based on the fluctuations. So this, I mean, this is really bijective. That means it doesn't matter what you use in a sense. And that, of course, we continue with the H approach.
Martin, can I ask a question?
Sure.
I don't understand your subscripts I. Are you using the summation rule?
No, that is just I0, I1. It's just I, J, K, and so on. Sorry.
Yeah, so the second I should really be a J?
Yeah.
All right, thanks.
Yeah, sure. No problem. Yeah, good question. So it's really tensor. Okay, well, that we might skip here. That is just, I mean, how you do that from PDF approach. This is the PDF, by the way. That is, so to say, a classical. Also, this PDF, of course, is a linear equation. That's Lundgren's PDF equation. You will not find that in too many textbooks. It's a linear equation. It has ugly terms. It's also an infinite sequence of equations. I come back to that later. However, just to let you know, any moment that you derive of this PDF from the Lundgren form will be an H quantity, not the R quantity. Anyway, now let's move on to turbulence and symmetries. One of the most important findings that we had more than 10 years ago was the following. Let's concentrate again here on this H equation. This equation is in fact in conservative form, right? Everything is under derivative. Remember, this R formulation was not. I mean, we have this complicated nonlinear terms. So this H formulation is a conservative equation, and it's linear. It's infinite dimensional, but linear. Now, what we recognize is because it's a linear equation that we can rescale all these H's no matter what tensor order. They all be scaled with the same quantity here. So we call that e to the ASS. So it's what we call a statistical scaling. Same for the I here, for this, that is the pressure term. And what we found, in fact, in this 2014 paper, this defines a measure of intermittency. And that is, I will probably try to explain very quickly. It's not so easy to understand, but I will try. So for this H formulation, the scaling is simple according to that H formulation equation. Now, what one can do, and is that what we did in this 2014 paper was Marta Wacławczyk, we derived the corresponding PDF. So this is the PDF formulation of this symmetry. And what you find is the following. Well, this factor here appears again. So suppose, well, yeah, just leave it. Now, what we see is that you essentially map a PDF to a new PDF. That is what symmetries are about, and that means it's a symmetry. However, what you see here is that in this mapping, it involves a delta function. A delta in the PDF means a constant velocity. So this mapping here essentially is equivalent to this type of a signal. So you do have a turbulent signal, then you have for a while a constant one that determines, so to say, the delta here. Then we have a turbulent one, and we have a constant one. So essentially, what you see is something of this sort. So you have a kind of a delta plus, so to say, a broadband PDF distribution. And that is the reason why we were saying that this symmetry here is a measure of intermittency, right? So that is essentially what it says. Well, let me go on. We found also a second symmetry, which is also very important. And that comes due to the fact that the Navier-Stokes equation is a conservative equation. And because it's a conservative equation, also the H equation is conservative. And that means all the terms are here under derivatives. That means you can add a constant to all the tensors here, right? I mean, you can just add something here and the constant will disappear because you have a time derivative, or here you have spatial derivatives. Also, this one here, it took us quite a while, some years, to understand what does it mean in terms of physics, because that's kind of odd that you can add something. And what we found is this symmetry defines a measure of Gaussianity, and that is also described in this chapter here, in this paper. And maybe I just skip that part here because it's kind of lengthy. But essentially what it does, it tells you you have, so to say, a PDF, you add, so to say, a kind of a free function of the form psi, and that is a symmetry that maps you to a different PDF. So non-Gaussian, hence non-zero high order moments, skewness, flatness are, so to say, induced by this type of a PDF, which is important. That means what we have in our hands is something in terms of symmetries, quantities that, like intermittency or non-Gaussian behavior, that are mirrored by this, what we call statistical symmetries. These symmetries, which I just showed to you, this one here, this rescaling of the moments, and that one here, this adding of the constant, has no corresponding one in the Navier-Stokes equation. It's a statistical quantity, and I have to say, when we first recognized that, I thought that is not physical, and we just ignored it, and we said it's kind of a, so to say, unphysical behavior. But now we believe it's a key quantity in turbulence. Okay, now let's look at data and DNS. First, I would like to tell a little bit more about the DNS we did. So the paper, that's a pure Poiseuille channel flow, pressure-driven flow. The DNS was up to Reynolds 10 to the 4, Ari tau 10 to the 4. It was recently published this year in Physical Review Fluids. The code is based on the one by Hoyes and Jimenez from 2006. It's essentially a Fourier in x1 and x3 direction, compact finite difference, and the time stepper is Ron-Kutta. Most of the computations we did was done at Supermuck and LRZ in Munich. It took us about 60 million CPU hours to get that, to get reasonable statistics, but we see later some of the statistics are still not good enough, so we actually got another 50 million CPU hours to continue. Now, just a comparison to classical DNS here. This is the old Hoyes Jimenez one of 2006. It is Reynolds tau 2000. I think that was a Japanese group, I think, and that is Lee and Moser 5200 from 2015, and this one here 10,000 is ours. In terms of numbers, we slightly coarser in all three directions. Also, the box size is smaller. I come to that, or you may ask questions, but that is, so to say, what we published. Also, the data is available on the internet. You can find it. We also compared the flow experiments. We looked at 3 different data sets. 2 of them were from the Center of International Cooperation Long Type Experiment, CICLoPE in Bologna. That was essentially the group of Alessandro Tolomelli. And also we looked at data from the Superpipe facility at Princeton. So we had, and in fact, this set of this CICLoPE1 here was actually done by Spencer Zimmerman and Joe Klawicki. They do different measurement devices. So this is multi-element hot wire, and of course at the Superpipe they have their own step hot wire devices to do the measurements. Reynolds tau is between about 2,000 and 49,000. Okay, now let me go to see what we do learn from all what we have seen so far. What I will be doing is we will focus, as I said earlier, we will focus here on the center region, and then we also look at the near wall region for the DNS, and we will look at the pipe flow experiments, essentially also the center region and the near wall region we will look at and see what we find. Well, as I said earlier, the theory is fully multi-point. However, what we will do later is essentially focusing on one-point quantity. We have not done multi-point yet, but that is no principal problem. It was just a matter of time and resources to do all the calculations. Just let me remind you what we will look at. We will look at the mean velocity. We will look at the higher moments. They all only depend on x2. That is hij, and then of course we go to higher moments. And let's look at what type of symmetries we have. Remember, we have scaling of time. Time, of course, does not appear here, but still we have scaling of time. That is AST. We have scaling of space. That is ASX. In the velocity, we have, of course, this ASX and AST. And now remember, we had this ASX, which also appears here in the higher moments, that appears linearly also here. For the scaling of, so to say, space and time, of course, that gets a factor here. It's kind of a square of this factor, or here the nth moment has an n times this factor. However, remember, this one is the same factor for all of them. The second thing here is this translation in this function space, right? This was also a statistical symmetry, so you can add something to the velocities and also something to the higher moments. There's also translation space. That's not so important here. Now try to remember, we had all this symmetry. Remember the heat equation. You could combine symmetries and you can construct solutions. And that is essentially what we're doing here. And now we make a major step. I will not be able to explain how we get to these equations, but we can interpret that. So what we find now is this set of equations here. And this set of equations, any solution to this set of equation is an invariant solution. Remember the heat equation, you know, where we had this invariance, and then we can construct this invariant solutions, put it in the equation, and you find that works okay. You can do the same thing here for the moments. So you have essentially an equation for the mean velocity and anything that goes to any order of the nth moment of the velocity. Let's focus for a minute on this equation. This equation looks pretty similar to the original equation that was written down by von Karman and Prandtl. Now, if you take that factor here to 0, assume that one is 0, you essentially have a constant here, you essentially have x2 down here, you have scaling factors. So this one here is essentially what von Karman and Prandtl wrote down. And we see in a minute why that is in fact almost the same thing. So they had this very deep insight into the problem. So what they essentially found is the condition for an invariant solution. We have to check in a minute what happens then. Why does this factor go to 0? And we can see that in fact on the next page. Oh, hold on. Well, I mean, then you can, once you have that, you can integrate this equation and then you get to any higher order moment. Now let's start with the log region. Let's start with the log region. What did von Prandtl and von Karman and Prandtl say? Well, they were saying the key quantity in the log region is u tau, right? If you go back here, everything essentially based on u tau. Kappa is non-dimensional, all that is dimensional. So the only dimensional, so to say, constant quantity is the u tau. In terms of symmetry breaking, u tau is an external quantity. The friction here is say, a symmetry breaking quantity. Now that means we can no longer scale the mean velocity. That means this exponent here goes to 0. And now we are exactly where von Karman and Prandtl were. If you put that to 0, that means you can no longer scale velocity. Well, you are actually back to the classical equation. You integrate that use the classical notation, well, you can just add the constant here, which is not so important. So essentially, the key quantity that they introduced was really the U tau. Now, using this fact here that this is 0, also for the higher moments, you can do that. You just rescale things a little bit, and then you find something interesting. You find a power law for all the higher moments, so n equal 2 and higher. You find a power law, and there's only one constant in here, that is this omega here, and that somehow depends on these parameters here, not so important. However, what is important, that, so to say, the moments are all coupled. There's only one quantity of the second higher moments that determines it. Also, we can say something of the prefactors and this Bn here in a minute. Now, start comparing that to data. This is essentially our DNS data. On the left-hand side, we have what is called this indicator function. That means when you put a log here, that is a constant. And people have done that for decades. Now, if you look at this, is the older DNS here. So the black one is our DNS, and you see a log law probably, well, Sergio says for the first time, between something like, I would say here, 200 and maybe 2,000, 2,500 or so. Numbers are pretty similar to the classical DNS, so the kappa and the B are almost, does not change much. Now, this is, I would say, the first really new and interesting result. And that is the lines here are the power law. This is the power law. This is a log scaling. This is also log scaling here. This is a DNS data, and we've tried to fit in the region where the log was valid. So between, over here, we were a little bit more careful, between 400 and maybe around 3,000. That is where we believe that the log is okay, up to here about. And it seems to work okay. However, you have to be careful. I mean, we have an enormous stretch here in values. So to be more better see whether that is true, let's try to express the exponent from the data. And that is what we did. This is just, so to say, an indicator function for the moment, for the algebraic moment law. So if you put that in here, you will find the exponent. However, we also did that for the data. And that is what we see. In the region between 400 and around 3 and 2.5, 3,000, we do see a fairly flat region. In fact, so to say, scaling with the exponent, with this n here, and this omega was given here. The omega is around 0.1. So when you have a 3 here, that will be 3 is 2, is 0.2, and so on. That is what we believe, and that is what we see. That is what we see in the DNS data, but also later we see that in the experiments. Well, interesting enough, I didn't talk about that one here. We could show that these are exponential functions of n. And so we took the data for Bn and Cn and Bn, which we see, and that is just the data from the DNS data. And we do see this is a log here, this is linear. So we do see very clear exponential behavior for these prefactors here. There is a reason from the symmetry theory why that happens. I'm not going to detail here. Now we come to the pipe flow, the data, experimental data. That is what they see. I mean, essentially they see the log here between, well, depends on what you like, but maybe 200 or 300 up to down here. You have to be careful. There's quite a number of different Reynolds number here, but the highest Reynolds number goes pretty high. It goes up to 10 to the 4. So that is fine. That is known. That is Superpipe. And now we also looked at the higher moments. So we tried to compare that, and it looks very good actually. And what we see is also the number of this omega, this one here. This is slightly higher, is 1.1. We had 0.11 and we had 0.1. So that works okay. You can also, this indicator function, of course, it has more fluctuations than the DNS data, but it works okay. It's 0.1, 0.2, 0.3, 0.4, and 5. And so on, that works okay. Also in the region where the log applies. And also this exponential behavior of the prefactors here is visible in the data, and also these numbers are similar. Now let's go to the deficit region. Let's look at the center part. The center part here is not yet clear. We know that this is what we call the deficit region. What we do now is the following. We say, well, this is no longer a constant. There is, so to say, the option to scale velocity. And we just integrate these, essentially infinite number of invariant solution conditions. And if you do that and rewrite that in this, what we call deficit scaling, that means the center line velocity minus the velocity scaled with u tau. This, of course, then is the second moment at the center line minus the second moment somewhere else. Also this one here. And what it essentially gives us, we do find a power law sigma 1. We do find sigma 2, but we find a general version of it. We find that there is a kind of a linear scaling in the center region of the flow. Now let's look at data. And first we looked at DNS data. And we also had the data from the older DNS, that is 2004 and so on. And what we did, we just did a semi-log plot. So this is mean velocity deficit, second moment deficit, log scaling, log scaling. Here is the wall, and here is the center of the channel. And what we did is we just compared, we shifted, this is our data here, this is some older at lower Reynolds number. And what we see, they essentially all look completely parallel. So there's very little Reynolds number dependence here on the sigma 1 and sigma 2 for the first and the second moment. You can see the numbers here, they are very, very close. Also, the prefactors are close. Now, we did not have for the older Reynolds, the older DNS, we didn't have the higher moments, but of course we had them from ours. And that is what we see here for our data. So now what we're plotting here is the nth moment in deficit form, in log scaling and also log scaling here. Again, this is the wall region. By the way, this region here is the log region. This is all log. This is towards center region. This is the center of the channel. This here is, so to say, the scaling law that we derived. And now we find something interesting because sigma 1 and sigma 2, they're almost the same value. If you look at them from the DNS data, they're almost the same. That means the exponent here, the exponent for all the moments is just a constant. And if you have a constant in the exponent, not depending on the moment, compare a homograph, that is what we call intermittency. It's a strongly intermittent behavior because it's a non-dimensional type of scaling. It does not depend on the moment, but it's essentially similar. If you trace back where that comes from, it comes from this symmetry that what we call intermittency symmetry. Also here we find these prefactors here, exponentials, that also comes from the symmetry theory. DNS give that very nicely. That is not so important. We also do similar things here for the data, for the experimental data. It was kind of tricky because they usually don't measure numbers here on the center of the pipe. Anyway, we did some kind of guided guess, so to say, what the center value is. We did some extrapolation. The theory essentially gives the same value. Even numbers are similar, even though it's an axisymmetric flow problem. So even there, this number here is essentially 0. That means strong intermittent behavior in the center of the pipe. Even here, the prefactors here look okay. That is very close to all the different pipe flows. Okay, so let me just do a final remark and some closing here. So far, we have only looked at U1 moments. So the question is, what happens in the center region moments for U2 and U3? There were criticism on this H moment approach because people were saying, well, the mean velocity is strongly dominated by the H moments are dominated by the mean velocity. And of course, that's true. There's no doubt about it. You could sort of say approximate this H moment to leading order with the nth moment of the mean velocity. So the question is the scaling we see really dominated by the mean velocity, or is something else going on? So what we did is we look at the theory, and the theory essentially tells us that even for U2 and U3 in the center region, we get this power law scaling behavior. However, one have to be careful. We have not published it yet. The problem is that U2 and U3 moments converge very slowly because the mean velocity is missing. Any quantity that has not a mean velocity usually converges much slower. So even odd moments converge extremely poorly. And for U3, you can actually formally prove that all odd moments are exactly zero. So for the next slide, we have to be a little bit careful. So what we have done here again, this is, so to say, deficit scaling of the moments here of U2 and U3 velocity. This is again log, this is log, this is near wall. So anything here is near wall region, and here we go to the central region. So what we essentially see is already at the low convergence, very low convergence rate, we can very clearly see that this power law behavior is exactly the same as for the U1 quantity, even though this one here does not contain a mean. So this is second, this is fourth, this is sixth. As I said earlier, the odd moments for U3 are exactly zero, at least in principle. Also in the DNS data, these numbers are much lower. And because we don't get this very smooth behavior as we see for the U1 moments, we decided to write a proposal, and that was just granted. We just started running new DNS to get better convergence of these moments which don't contain the mean velocity. A final word on Reiner stresses. The question is, how good are the H moment scaling for stresses, right? I mean, we essentially looked at these quantities, how we stressed the moments. Now the Reiner stress value U11 is this one, is essentially this one minus the mean velocity squared. And what we did is we just played with the numbers, and we needed just some very small adjustment of the parameters. And that is what you all know probably. This is the usual U1 squared moment based on the fluctuations, of course. This is the usual thing, and people believe that is, or others believe it's not. So we do see where others say this is a log region here, maybe. I don't judge here. However, even the theory for this, so to say, reduced moment, which is a Reiner stress moment, we can do a pretty good job in terms of mimicking the results. One thing that we're just heavily working on right now is the PDF scaling laws. So a complete analogy to the moment scaling laws. PDF scaling law can be derived from the statistical symmetries. So essentially this here is a solution also for the higher moments, for the higher points to Fn. This is a solution to the Lundgren equation. It's probably the first solution ever generated for the Lundgren equation. It's a similarity solution, of course. What we already showed is that when you take moments of that, we get exactly the scaling laws that you saw earlier. So we can recover all the scaling laws, but we want to compare these results here with the DNS data. That hasn't been done yet. So I guess I come to my conclusion. So the basis for the analysis is what we call this H moments here. There are conservation laws. It probably makes sense to look at these things. A set of statistical symmetries have been derived. I mean, they're kind of hidden in Navier-Stokes equation, but they're very important. They're mirrors. This mirror key properties of turbulence, intermittency, and non-Gaussianity. They're key ingredients of classical and new high moment scaling laws. These statistical symmetries give rise to anomalous scaling. And I think three things I would say are important for me. Scaling laws are invariant solutions of the infinite multi-point moment equation or the PDF equation or whatever you like. So scaling laws are not something that you just cook up and they're just curve fits. They're solutions of something. That is important. Scaling laws can be derived rigorously from symmetry arguments or symmetry theory. And scaling laws are becoming particularly simple in this, what we call this H formulation. Now, for example, we're doing right now a very large DNS on a jet flow, used the whole machinery, which is of course a flow without walls. That works extremely well. And I would probably stop here. Thank you for listening. It was a pleasure for being here today. I'm happy to take questions. And the results that I showed are heavily based on these two papers. That was, no, I'm sorry, that is wrong here. That is PRL. I think it was flipped here. That is PRL. This is PRF. That is, yeah, well, I can just correct that. And data are available if you get these papers here. There's a link to these data sets. Thanks a lot.
So thank you, Martin, for the very interesting talk. So I would say let's open the discussion. So whoever wants can just ask a question or write it in the chat. Just feel free to unmute your mic and ask a question, or write it in the chat and I can report it.
So Martin, I'll start. This is Jim. Oh, Alan's got his hand up. Alan, you go.
Okay, thanks. Lots of interesting points, Martin. One question. Now, the intermittent behavior you showed depends on sigma 1 and sigma 2 being equal or almost equal, but that's just an observation of data. That sort of puts the onus on some kind of theory to explain why that near equality should hold as a way of identifying the underlying origin of that intermittency. I don't know if has there been any progress or thought on that?
Probably I did not fully understand your question. I mean, let's go back to the formulas, I guess. Maybe, I don't know, this one here, is that okay?
Yeah.
I'm sorry, I did not fully understand your question. Sorry for that.
The DNS shows that the value of the difference is almost zero.
Yeah.
That's just data.
That's true.
But it leads to a very interesting implication of intermittency, which means if we're looking for a truly theoretical origin of the intermittency, we'd have to have some understanding other than just observing in data.
That's true.
That the value is almost zero. So that, I'm just saying that you've raised a question or a challenge to theorists to say that, to identify some underlying reason why this should be true.
That's true. Well, the thing is the following. I mean, we're actually working on some theory. We're trying to figure out where these numbers come from. It's not so simple as you can imagine. Let's go back to this one equation here, which I had at the very beginning. This one here, maybe. Or maybe it doesn't matter. What we see here is, for example, let's take the kappa. I mean, we also don't know where the kappa comes from, right? It's just a mystery. I mean, it's around 0.4, but we have no clue. The thing is, if you look where it comes from, at least from the symmetry theory, you observe that one here is out because it's zero. That is, so to say, the argument. And now the kappa essentially is that quantity divided by that one here, right? I mean, that is essentially what it does. I mean, if you just put that out, I mean, you just essentially the kappa is somehow hidden in these two, what we call group parameters. So at least we do know where these scaling parameters come from. They come from group parameters. But and you correctly say, at least this point, we do not know what determines the values. However, I personally believe, and that is the reason why we go into the PDF now, that we get a better handle on this question when we go into the PDF, because they appear in a very similar way there. But I cannot tell at this point.
Right. Well, it's not critical for any qualitative behavior, whether it's kappa is 0.4 or 0.3 or something else. I mean, it's interesting to try to find a basis for the number.
Yeah.
But in fact, it doesn't really matter what sigma 1 is by itself.
That's true.
It's really the fact that sigma 1 equals sigma 2
Yeah.
that has a major implication
That's true.
qualitatively, and so it raises a different level of
That's true.
theoretical
That's true.
interest. But
That's true.
that was my only point.
Yeah. No, I understand. Thanks, Alan. By the way, I owe you an answer to your email.
Sure, that's fine.
You
Whenever.
will get it.
Sure.
So I think there was Jim Brasser, and then Jim, do you want to ask a question? If I'm not wrong, you were.
Yeah, I had a couple of things I wanted to discuss with Martin. So Martin, if I'm understanding, you began with the point that the classical scaling arguments are just basically dimensional analysis type of analysis. You start with reasonable hypotheses, the key ones being that the key velocity and length scales are the friction velocity in the surface layer, the friction velocity and the distance from the surface. And then you wave your hand about, make some physical arguments about why those are the dominant scales. And then you scale the mean velocity gradient and you get the log layer. Okay, so that's the way we generally teach this. And you made the point that it's not directly tied to the Navier-Stokes equation. That was one of your early slides. Of course, that's true, but I'm wondering in this symmetry approach that you take, I guess I'm asking, can one also say that it's only indirectly tied to the Navier-Stokes equations in the sense that you determine, symmetries based on the Navier-Stokes equation? So there is a tie there for sure.
Yeah.
But all the rest of your arguments are based on symmetries. They're not directly tied to the Navier-Stokes equation. Did I get that right?
No, that is absolutely right. I mean, one has to clearly say that. I mean, the symmetries, so to say, give us a certain hint where a thing might apply. We have looked at a variety of different flows, also rotating flows. So you get a good hint where to look for the scaling behavior. But you're right, scaling laws, and that is also still true for this approach. Scaling laws apply only in certain regions. And a priori, we don't know where. So the only thing I can claim is I have the multi-point moment equation. I can construct solutions, but at the first place, I don't know where they apply. That is true. That is absolutely true. So I have then to impose a physical argument based on symmetry. I mean, the most simple one is this log thing that it applies in the log region. So in that sense, yeah, you're right. I mean, we have not a full series, so we cannot solve from the one wall of the channel to the other wall. We cannot give an answer to the entire region between these two walls. We cannot. That's true.
Right. So, okay, so that being the case then, if we go back to sort of the classical argument that in the surface layer, the only or the dominant characteristic scale, it's the length scale. There obviously there's other length scales. There's the viscous layer scale. There's the distance, the boundary layer scale. But the argument is that the local scale, length scale, which characterizes the integral scales, is the distance from the surface, and that the other scales take a subservient role. That they're suppressed relative to that scale. And from a physics point of view, that's an important statement. And it's a similar thing with K41 and so on. We make the same kind of hypotheses, and then it turns out that you get results that are consistent with data and so on. So does your scaling argument provide some additional understanding of why that one length scale, the distance from the surface, is the dominant one, and the others are much less strong and therefore can be dropped out of the scaling argument?
That's a good question, actually. I mean, it would then be, of course, an asymptotic argument, which I haven't done here yet. No, I mean, one has to be honest. I mean, yeah, one could extend it somehow and say, well, what would be the Kolmogorov length scale? What would the importance there? We haven't done that yet. No, we have not. So, but I would say one would probably still have some physical argument to get away with that. I mean, And I don't want to do that.
Okay, well, I mean, that's the kind of arguments we make, right? We make physical arguments, and then we test to see whether the arguments lead to sensible results. That's the classic approach, and there's nothing wrong with that approach. We're just trying to understand the consequences, and I was hoping.
I understand. So, well, we haven't done that yet. No, that's true. But for the log, it's definitely true. I mean, what I'm using here is the distance to the wall is the key quantity. Yeah, that's essentially what's in here. Yeah.
Right. Right.
And just a point regarding this that's kind of so basically if we want to take the problem from the other way around, like we can use the symmetry arguments you derive to test if a physical argument for scaling is consistent with the symmetry allowed by the solution. Or on the other hand, we can disprove a scaling eventually.
Yeah, that's right. Yeah.
Okay. Okay. Sorry for interruption. Right. Go ahead.
No, that's fine. We're just having a discussion. I have more discussion points, but others need to speak before I continue. So I'm going to go away. Thanks, Martin. Take care.
Yeah. Thanks for the presentation.
Can I quickly jump in here? Since hello, Martin. This is Christos.
Hi, Christos. Good to see you.
You too. Exactly this log law that we were discussing before. You're obtaining for symmetry arguments and symmetry breaking arguments, which should be valid some part of is for some distances and not for other distances.
Yeah, that's true.
Well, I mean, you know.
Oh, why that is the case?
Yes, I mean,
yeah. Well, I mean, that's a good question. So why does the log law not go further into the, so to say, the bulk of the flow? I mean, that would be a good question. Yeah, that's true. I don't know. Yeah, no,
but the symmetry imposes it. It should be there. The symmetry is valid whatever the distance from the wall. I assume.
That's true. But I mean, well, we have looked at many different flows, and I mean, turbulence does the following. That is, so to say, the bottom line. What we see, turbulence likes to establish as many as possible symmetries that it can, so to say, get from the basic equation, so to say. Except if you have one strong quantity that is breaking a certain symmetry, and then of course it loses it. For example, rotation is such a case. I mean, we have looked at rotating flows, of channel rotating flows. The rotation is introducing a time scale or an inverse time scale. It breaks it. And then, for example, the center region looks completely different. So the bottom line, that is at least, but that is not, so to say, in mathematical formulas. Turbulence tries to get as much as possible symmetries, except in a region where a certain scale is imposing and breaking it. That is, so to say, my lesson learned from the last 20 years.
You mentioned Reynolds number going to infinity. Are you symmetries of the Euler equation or the Navier-Stokes equations?
That is Euler. What you have, that's not a big problem, because that I haven't shown here. You can do an asymptotics for, essentially you can do a boundary layer type of asymptotics for the multi-point equation using the Kolmogorov length scale, and then so to say, you get an equation on the order of the Kolmogorov scale, and you get an equation of larger than that. And the larger than that is essentially admitting the symmetries of Euler, while the other one is more complex. I didn't show that here, but that asymptotic is actually published. We did that. So you have to look at anything that is larger than Kolmogorov length scale, then you find.
So you have symmetries for Euler and symmetry breaking from the wall.
Yeah.
Where there's viscosity.
Yeah, sure.
So is that consistent?
Yeah. Well, I mean, the viscous sublayer or the buffer, well, actually we looked at the viscous sublayer. I forgot what we got from the data, but I think it's kind of simple. But here we didn't do that. I mean, we did not look at anything where local Reynolds number is small. We did not, no.
Mm-hmm. Yeah.
Okay, I'll stop. Yeah, Mikael.
Yeah,
Bye.
Yeah. Thanks, Christos. Hi, Mikael.
Hi, Martin.
Hi, good to
Very
see
great
you.
to see you, and
Yeah.
thank you very much. Thank you very much for your talk. And first of all, I would like to reply to Christos. In fact, the Eulerian equation, they are invariant to classical group transformation, like translation, rotation, and scaling symmetry, the main important. And Navier-Stokes equation destroys this symmetry transformation because of the viscosity. Here is the same. You have the wall which destroys the symmetry, and so that's why the influence, the domain of this destruction is the length of penetration of log domain. Yeah, this is
maybe that is a physical argument.
Yeah, but Martin, again, like in Marseille, they say same fish for the same price. So how to imagine, because I have really difficulty to imagine the application of symmetry group transformation to the averaged equation, because for example, averaged equation and instantaneous equation, they have different symmetry properties, like, for example, Boltzmann equation and Newton equation. So they have, but Boltzmann equation comes from Newton equation, but they have different symmetry properties. So that's why I was thinking that we can apply the symmetry properties to the instantaneous field. For example, like you have a photo, you just expand it or compress it, or you turn it, and so on. Done statistically, you have equivalent results. And because it can be shown that the composition of three fundamental group of symmetry transformation is equivalent, in the case of the Navier-Stokes equation, is equivalent to the transition of the small scale of averaging to the larger one. So, and the question is how to imagine the scenario when you have the symmetry transformation in averaged, in already statistical averaged equations. What should I show? This is instantaneous, this is classical, and in fact, what you show here, this is the application in order to find the so-called intermediate or solution, auto-similar, self-similar solution. This is the result or the objective of the group symmetry transformation. But it is not averaged. It is not averaged equation.
Well, you're making an extremely good point, actually. Thank you for that. And the point is the following. Let me just repeat that in my words. Mm-hmm. If you have a physical process, like, I mean, the collision of atoms, and mm-hmm. so, I mean, they just follow Newton's law. Mm-hmm. Now, if you then make the step to Boltzmann, mm-hmm. in fact, I got just 2 weeks ago or 3 weeks ago, I just gave a talk on that in Javier's causality workshop at Madrid. So what essentially happens, so if you look at this single, so to say, motion of a molecule and the collision, mm-hmm. and now you take the averaging, then you essentially go to Boltzmann. And as you said, you get more symmetries. Mm-hmm. Even further, now, if you take Boltzmann and you, for example, from Boltzmann, what we can learn is, for example, we can derive the viscosity law, Newton's viscosity law. Also, Fourier's heat conduction law comes from Boltzmann equation. And the Fourier's conduction, heat conduction, essentially leads to this equation here, right? I mean, the heat equation for, say, a non-moving gas, so to say, heat conducting gas. Mm-hmm. So the thing is, and this equation in fact has many more symmetries. I only showed 2 of them.
Yeah, sure.
As in total, it has 6 symmetries.
Mm-hmm.
One of them is very complicated, and it gives rise to the fundamental solution of the heat equation. So the bottom line is, whenever you take a fundamental physical process and you take some kind of averaging, and I would say in a good manner, you usually gain more symmetries. That is the bottom line of what I was talking about at that workshop.
Mm-hmm.
And that is also what we see in turbulence. But I'm not sure if somebody ever has written down, probably somebody has done that, but it's known in physics for a long, long time. Take a single, so to say, physical thing and make it large. You will find more symmetries. Also, for example, in phase transition, where they find is what they call the conformal group, which is an infinite dimensional Lie group.
Yeah.
The basic the basic things are really on the atomistic level has very simple symmetries. But so to say, the phase transition process then, of course, has this conformal group, which is much wider than the classical things that we introduced at the first place.
Mm-hmm.
So in a sense, I would say this is something very, very common in physics, that this happens.
Okay. Martin, may I have another small, very short question?
Sure.
What is the Reynolds number in your intermittency? Because for different Reynolds number, you have different intermittency.
Yeah, that's a good question. I don't know. I cannot say that.
Mm-hmm.
So, I mean, I haven't looked at this into very much detail so far.
Mm-hmm.
We're actually right now working on homogeneous isotropic turbulence and try to, so to say, use the whole machinery of symmetries to essentially this so to say, most simple sort of set of equations. And then probably we will be able to answer that better looking at this much simpler flow, I would say.
Mm-hmm.
But I cannot tell. No, sorry.
Okay. Thank you, Martin.
Well, I have to
thank you again. Yeah.
Can I quickly follow up on one more question, Martin?
Yeah, sure.
The data you showed DNS and even all the way to Superpipe, and you showed the how do you call this? The indicator function, which should be equal to 1 over kappa. It's actually never equal to 1 over kappa. It always goes up and down around it, and all the data show this. All the data. Does it mean that the symmetry is not valid? Symmetry implies 1 over y. 1 over y absent implies no symmetry. You always have this oscillation.
Yeah, I tell you what, but
in Princeton at Arita 100,000.
Yeah, you're probably right, actually. And you know what we can do? We can actually say, why don't we just assume that this is a power law? That we can do. And then of course this one would look different. This we probably could make very flat, actually, very flat, as you would like to see it. And then it would no longer an exponent, a log law, but it would be a power law with a very small exponent. For the rest, I mean, for the higher moments, it will probably not change much, a little bit. But yes, I mean, in that sense, probably Barnblatt was right. And he was at Stanford when I was there, when he published this paper. Well, maybe it's a power law. I mean,
what symmetry would that be then?
Well, then, I mean, the symmetry breaking argument would not be so easy anymore, because when you go back here, it would essentially mean that this thing here is not exactly 0, but it's a small number. You can just do this, crank the angle and get something similar out of it. You would then get here a power law with a very small exponent. And here I would guess you would get something similar where there is this, I call it epsilon, this small exponent, where the epsilon would appear somewhere here. Yeah, that is doable. And that, I mean, well, take the data and see if that works. That might work, yeah. No, I agree. I mean, that there's a constant appearance of this kind of little wave. Yeah, that's true. I agree.
Okay. Also, to respond to Michael's point, indeed the viscosity would be near the wall, but further, the log law ends at some point away from the wall. If it was for the reason that Michael said, it would not end there. So I still think there is a problem with mixing Navier-Stokes and Euler. Anyway.
Anyway.
Okay. Thank you. Bye-bye.
Yeah, thanks, Christos. I think there was another question here. Francois had raised his hand.
Yes, because you mentioned intermittency, I wonder what is the definition of intermittency that you are using. Are you speaking about like multifractal properties or non-Gaussianity? I believe here you speak about non-Gaussianity, perhaps.
Well, I mean, let me just go back to that little picture here. Give me 1 second. Here we go. Well, I mean, I honestly, I've never worked on intermittency. It was just curious that when we found this type of symmetry in the moment equation, that we could derive a similar one in the Landkin equation. I mean, and then we recognized that because this is a delta function, that a delta function in probability space means a constant value, right? It's a laminar flow. So, but I mean, we discussed that with Marta, who was the first author on that paper, who actually did the calculation for getting from this one here to this one, which is not so trivial. Because in turbulence, I mean, there is this external internal intermittency. I mean, she was not so happy with this picture here, but I kept it anyway because I said it's simple. But you're right. I mean, and I'm not considering myself an expert on intermittency. It's just an observation that this kind of mirrors a certain type of intermittency, and that is probably more the external rather the internal one. Okay. That is my, so to say, view on it. Maybe you have a better explanation. I don't know.
I don't know, but yeah, I was puzzled by the definition that you are using, because I saw your paper about it, but I wonder the reason why you speak about intermittency.
Yeah, it's just that I mean, if you assume that this is, so to say, really a broadband PDF of a turbulent flow, and you add, so to say, or you subtract, so to say, this delta function here, then of course you would see something of the sort that we see down here. I mean, you have the PDF, a broadband PDF, plus the delta, and that is what I would call an intermittent behavior in the flow. That I mean, it would be probably one definition, but that is probably the one I would introduce here for our observation. I'm not sure if that makes sense to you.
Okay. Yeah. Thanks. Yeah.
So in this context, then you're taking the PDF with the delta function and you're imagining a signal that looks like you drew, but you could imagine other signals that have a spike at 0 in the PDF as well. They don't have to look like that, do they?
No, definitely, absolutely, absolutely. No, that's definitely true. It's just one example. I mean, you're absolutely right.
Okay. Let's see if there are other questions. So just once again, just feel free to, yeah, Alan, go ahead.
Oh, there's Ellen Kirsten. One more question.
Let me see. I was a little bit puzzled about the discussion as to why doesn't the log law go all the way through the flow? And of course, it can't go past the point where its velocity value would exceed the centerline velocity. So, and therefore you have to go to the law of the wake, or the version of it that you described. Is it a question of the log law ending at a velocity that's asymptotically small compared to the centerline velocity? Because that's the only thing that I would consider sort of a non-trivial kind of premature termination of the log region. And in any case, is there data that could even test such a thing at an appropriately high Reynolds number? So I just clarify, what do we mean by this issue of the log law not persisting as long as the symmetry might suggest?
That's a good question. I mean, honestly, I can't answer that question either. I mean, well, one could, of course, do that with the data we have, I guess. If let's go back to the plot here. Let me just see that. Hold on.
Well, you're looking, could I add to Alan's discussion?
Oh,
So
yeah,
Alan, if I'm superseding you, please, I'm sorry, you take it back, but is there some relationship between symmetry breaking? I mean, there's two boundaries, right? There's the wall, so symmetry is broken there, but there's also the other boundaries. So in a classical flat plate boundary layer, it would be the top of the boundary layer. In this case, it would be the other wall, where you could replace that by the middle of the channel. So is it an issue of symmetry breaking in two places, not just the wall, but also at the outer boundary of the boundary layer? I'm thinking, I guess, of a more traditional flat plate boundary layer.
Well, it's a channel, so you're right. I mean, you have the log on both. You have the log on both sides, and then you have the deficit in the middle. I mean, well, I mean, you have then the symmetry breaking due to the U tau, as we classically argue.
Yeah, but if this were a flat plate boundary layer, would there be symmetry breaking at the top of the flat plate boundary layer? You know, where the edge of the boundary layer lives.
Yeah, it will.
Yeah. So I mean, and is that sort of consistent with the physical idea that there are these large eddy structures that are capped by the boundary layer, and that in the outer part of the flow, they cannot be left out of the dimensional analysis, that they play an important role now? Is there some connection there? I
would sort of say only follow this discussion whether large-scale structures influence any statistical quantities only from the side. I never tried to make this kind of an argument, actually. So I cannot tell. Yeah, I know that people tried that and they see, well, there's these huge structures and they have a certain influence on the new wall. And
well, I don't mean the very large scale structures. I just mean the boundary layer bounded structures. The integral scales in the outer part of the boundary layers have not only, you know, in the surface layer, the integral scale on the distance from the surface, but in the outer part, they scale on the boundary layer depth itself. So that implies that those eddies have now become important in the scaling arguments. And I'm trying to tie these classical kinds of arguments, these dimensional analysis type arguments, to your symmetry arguments. And I'm wondering if it's a symmetry breaking. Is that the connection? The symmetry breaking introduces delta as the outer scale.
Well, yeah, it in fact does. I mean, if you go back, as you suggested, go back to a boundary layer. I mean, the integral, I mean, usually in the near wall regions at log, you have the linear growth of the integral length scale. And then in the outer part, you usually have a constant integral length scale. That is the classical argument for a boundary layer. And if you look at that, you can also crank the machinery, you get an exponential type of behavior, which I published in one of the very early papers in 2001 or so, that the outer part of a boundary layer is pretty close to an exponential because of exactly the symmetry breaking, because the boundary layer breaks symmetry of scaling of space. You have a length scale there. I'm not sure if that answered your question. I'm not sure if I answered.
Well, Alan, if I superseded your question, please carry on.
Actually, I like the fact that you brought in the flat plate boundary layer, because that's the boundary layer for which it's possible to, not just possible, but we have available data at sufficiently high Reynolds numbers to potentially address questions such as, does the log law appear to end at a U value that's asymptotically small compared to like the free stream U value in the case of you know, just a flat plate boundary layer. And that would be, to me, a good definition of the log layer prematurely terminating. Because if it goes until order one of the free stream, well, it has to turn over, because it's not going to have it's got to be a smooth function with continuous derivatives.
Yeah, I see what you're saying. I mean, essentially what you're doing is you look into this region here. I mean, what I'm showing here again is sort of say, this is different. I mean, this is the mean velocity here, the lower one. This is the mean velocity. This little part here is the log region. Well, I mean, but then it's kind of, well, not so clear. Well, so you're arguing, so to say, that this value here at the end of the log is small compared to the centerline velocity, which of course here is now in deficit. It's kind of not visible because that goes to 0. Is that what you're saying, right, Ellen?
Well, I'm asking the question. It's just an empirical question.
Yeah.
In other words, is there data right at this point in this state of knowledge? It can only be answered by data as to whether, in the limit of infinite Reynolds number, the log region ends at a mean velocity value that's asymptotically small compared to the relevant outer scale velocity, whether it's the centerline velocity in channel flow or the free stream velocity in the flat plate boundary layer.
Right.
It's an empirical question. That's why I like the flat plate boundary layer. You can look at potentially the data from the Utah salt flats or wherever.
The problem is a little bit, I guess, that you have to define, so to say, where does the log end, right?
Yeah.
And that you cannot really do on the plus variables because that strongly depends on the Reynolds number, right? So you have to go back to, say, the external length scales, and then you can say, well, the log ends 10%, 50% of a certain length scale usually. That is probably doable, not in the plus variables, right? Because that is the upper end of the log, and plus strongly depends on Reynolds number, right? So you have to go to outer variables to define the position where you take this is the outer edge of the log and take the velocity there, right?
Yeah.
Of course, the fact that you have to go to outer variables is a consequence of another length scale and velocity scale becoming important.
Yeah, that's true.
But for it to end prematurely, as you know, that was the proposition of the earlier discussion, it would have to end before the outer scale variable becomes obviously important.
Yeah,
so there'd have to be some gap there, some other, like no man's land.
Yeah, exactly. Yeah, that probably there is. Yeah, you're right, definitely. Yeah. Yeah, but that is our inability to describe turbulence from the one wall to the other one. You have gaps there. We have scaling regions. We have gaps that we're not able to give any, tell us any, that, well, to give any solution, so to say, whatever it means in terms of solution.
Yeah, well, as of my current understanding, we don't have evidence at this point whether there is even such a gap between the log law and the deficit law.
I honestly don't know. No, we don't know.
Right. Okay. Well, that was just my point. Thanks.
Thanks, Alan.
Okay. So let's see if there are other questions. Just once again, feel free to unmute your mic and ask the question, or you can just write in the chat if you have any. That doesn't seem to be the case, so maybe I can ask you a couple of questions. One is related to the two sigmas, which were like very similar, so they kind of cancel out. Yeah, that's the slide. Do you expect that this is kind of a feature that's somehow universal, or like when you go for like non-parallel flows, you expect them to be very different?
It seems to be that, but it's kind of probably too early to say. But we, as I said, we're just doing a very big DNS on a jet flow, and it seems that this, what we call this intermittency symmetry, that seems to be also play a major role there, at least in a certain region, I would say. Yeah.
Okay. And my second question is a little bit more like on the implementation side. Is it? I mean, for what I understood, based on one of your very first slides where you were comparing the H and the R momenta, this kind of symmetry argument could somehow open the way to like having a modeling approach which tends to model H rather than R, because apparently based on the equation which is supposed to be verified for H, it's much easier to model it.
We're doing exactly this. I have just one PhD who is about to finish. He published 2 papers. Actually, one just came out, and another one just started like half a year, maybe 9 months ago or so. We're doing exactly this. I mean, if you go, that's a good question. If you go back to, let me go back to Navier-Stokes. I had it somewhere here. Oh, where was it? Yeah, when you look at, if you look at turbulence models, or let's look at the history of turbulence models, starting with Princeton and von Karman, and you go until maybe the 80s, you will recognize the following. You will find that in terms of symmetries, every new generation of models had more symmetries, getting closer to Navier-Stokes. Then in the 80s, I mean, then or the 90s, we had some reasonably good Reynolds stress transport models, which actually had all the proper symmetries. However, we also have the say K-epsilon two equation type of models.
Yeah,
they have all the proper symmetries. They have the Galilean invariant rotation, scaling, blah blah blah. However, you will see they have too many symmetries.
Yeah,
these models say, let's stick with K-epsilon. They're insensitive to rotation. That means they have a symmetry that is completely unphysical. So what I'm about to say is, so if you go to the history of turbulence modeling, you will recognize, without ever saying that clearly, at least most of the papers don't say that clearly, they have implemented symmetries of Navier-Stokes, and now we are in a position that they're essentially there. However, from what we call the statistical symmetries, they're only partially, so to say, introduced, I would say, more by accident. For example, if you look at K-epsilon, you can find the log there. But the log needs to be, so to say, valid. Let me get back to the log. Where is it? Here, this one. That one you need for the log, but it's a statistical symmetry. This parameter here is related to statistical symmetry. Now, if you kick that one out, as we usually do, you see, and that's part of K-epsilon. So, so what I'm saying is, to some small extent, turbulence modelers implemented what we call the statistical symmetries. Now, group theory is a very constructive machinery. So you can actually say, I have only a bunch of groups, give me an equation out of that. That is doable. And that was published in our first paper. Then to make it really a good model out of it and to implement all these symmetries turned out to be extremely difficult. So I have right now a second PhD working on this issue.
Okay. So basically, as far as I understand, when you say that the two equation models or somehow the K-epsilon introduce the log scaling, that's because of the Boussinesq hypothesis, and then when you go to Reynolds stress, you get rid of the Boussinesq hypothesis, and then you move. That's the idea, right?
Yeah, that's the idea. And Boussinesq doesn't tell you anything about rotating flow.
Yeah, of course.
That is the key point. So it has too many symmetries.
Okay. Thanks. That was very clear. Thank you.
No, thank you.
Okay. So then thank you very much for replying to so many questions and for your seminar. That, as you could see, it was very lively. So that's
indeed. Yeah, very nice. Thank you for all of you. I mean, have very nice, interesting questions. That also inspired me to look at some other things. Well, anyway, thanks for listening. It was really great talking to you. I hope to see you soon in real life.
Thank you for participating and for accepting the invitation. So I hope to see you all in 2 weeks. Next week we will not have the webinar, but at the beginning of June we will. So hope you enjoy the evening.
Thank you. Take care. Bye-bye.
Bye.
Thank you.
Thank you. Bye.
Thank you. Yeah.